Well, in the last two classes, we have studied the principle of operation of chemical lasers. And today, it's the turn to look into the way a gas dynamic laser operates. But before we move on to the working of gas dynamic laser, let me once again go back to chemical lasers, basically to explain it to you some aspects of this laser that I forgot to mention in the previous class. This basically involves the experimental configuration used to affect operation of a chemical laser. Let us consider the case of hydrogen fluoride laser that we had described in quite detail. As you know that the chemical reaction between atomic fluorine and molecular hydrogen results in the generation of hydrogen fluoride molecule in its vibrationally excited condition, which of course serves as the light emitting species. And of course, atomic hydrogen is also generated in the process. While it can be a supply of molecular hydrogen is readily possible, but how do you ensure the generation of atomic fluorine which will set up this equation, resulting in the creation of the vibrationally excited hydrogen fluoride molecules? Actually, fluorine is essentially, atomic fluorine is essentially generated by subjecting high voltage discharge in sulfur hexafluoride gas. Much the same way, an atmospheric pressure CO2 laser operates. Such lasers, as you have already studied, are called TES CO2 laser, transversely excited atmosphere CO2 laser, where a high voltage discharge is applied transversely to the laser gas mixture. Likewise, here too, two electrodes are kept transverse to each other, and the electrodes are uniform field electrode to remove the possibility of any arcing. And the sulfur hexafluoride gas is kept in the inter-electrode volume, and a high voltage discharge is subjected to SF6 gas. In the discharge, you already know, you create an avalanche of electrons having a range of kinetic energies. Now, when electron with appropriate kinetic energy collides with 6 sulfur hexafluoride molecule, then if the electron has enough kinetic energy, it can actually utilize that kinetic energy to dissociate sulfur hexafluoride into SF5 plus atomic fluorine plus of course electron now moves with less kinetic energy, having supplied the energy of dissociation of SF6 into SF5. Now there will be many more electrons which will then collide with SF5 and dissociate it further into SF4 plus atomic fluorine plus electron. And this process will go on. Electron then collide with SF4, create SF3 and fluorine, and this will continue. This will create an avalanche of fluorine, atomic fluorine, which will be available to initiate this equation, which will form the active species for the process of lasing. Now, the typical configuration of such a laser would, in a very qualitative sense, schematically can be represented like this. This is the main chamber, which will basically comprise of two regions. The one region is, of course, the reaction chamber, which forms the active species, namely the vibrationally excited hydrogen fluoride molecule, and then the lasing zone. So, in the reaction chamber, the molecular hydrogen is readily injected into. However, the fluorine is created in another auxiliary chamber where SF6 gas is subjected to high voltage discharge. This is SF6, high voltage discharge. It creates atomic fluorine, which is then injected into the reaction zone, where it reacts with molecular hydrogen and generates vibrationally excited hydrogen fluoride molecule, which readily moves into the lasing zone, which of course comprises a cavity that contains the rear mirror, that is the mirror with 100% reflectivity, and a partially transparent mirror through which the laser beam would coupled out. And as this vibrationally excited hydrogen fluoride enters this lasing region, inevitably it actually spontaneously emits photons that will be emitted in all random direction, and some of this spontaneously emitted photon, which will travel along the axis of the cavity, will actually seed the stimulated emissions, and stimulated emission would eventually allow amplification of light, resulting in the laser beam, which will eventually be emitted through this partially transparent mirror, and the vibrationally de-excited hydrogen fluoride molecule then flows out of the chamber. So this is essentially the way HF laser would operate. Well, with this, let me now move into the laser that we are going to, the operation of which we are going to discuss today. That is, namely, the gas dynamic laser. Gas dynamic laser actually can be considered as a variant of chemical laser. This is because here thermal energy, instead of chemical energy which pumps a chemical laser, here thermal energy, which is stored in a gaseous mixture, actually is maneuvered to pump a gas dynamic laser. So how this happens? Well, we will try to gain an insight into that. But the different relaxation rates of the various energy levels of a gas are exploited here to create a population inverted condition. Basically, the temperature of the gas is first elevated to a very high temperature, and then this hot gas is subjected to a rapid expansion through a nozzle. This actually creates population inversion. Well, let's delve a little deep to gain an insight into the underlying physics which is responsible for the creation of population inversion and internalizing in such lasers. You see, how does it happen? How this scheme, the meaning you elevate the temperature and then rapidly cool it by letting it flow through a nozzle, allow to create population inversion. Well, for this, let's actually refresh our memory on Boltzmann distribution of population. Let us consider a gas, molecular gas, and let us assume n is the number of molecules, which are to be distributed among say two energy levels, one with a lower energy E1, the other with a higher energy E2, and the spacing between two, gap between those two energy levels is said delta E. So if N1 is the population at the energy level E1 and N2 is the population at energy level N2, then from Boltzmann distribution of population we know that N2 will be equal to N1 e to the power minus E by delta E by Kt, where K is Boltzmann constant and T is the gas temperature. This is equal to N1 by e to the power delta E by Kt. For any finite temperature, this is going to be more than 1, and hence N2 will be less than N1. That means as you go up in energy, the number of molecule in that energy state is going to be lower than the energy level which is located under it. And in the limiting case, we already know this. In the limiting case where T tends to infinity, then this becomes e to the power 0 or N2 becomes equal to N1. So even then, even if we have increased the energy temperature to infinity, even then at most the population of the two level becomes equal, yet you don't get population inversion. Now suppose you have now distributed these molecules among say many more levels. So for example, say this is E1, E2, E3 and E4. So this is N1, N2, N3, N4. So in the beginning, suppose a temperature is very low or maybe close to absolute zero. So all these N molecules which will be gone with, they will all be residing here. Now as you elevate the temperature, this population will now gradually go up into the energy level, but always maintaining the Boltzmann distribution. That means the higher energy level, population at the higher energy level will always be less than the population at the lower energy. Now, after you have elevated the temperature to a fairly high value, that means you have transferred large number of population to these higher energy states. If you rapidly cool it, and if you say that way you can create a state of population inversion, that essentially what you are hoping for that as you are rapidly cooling, then the population from these levels, then it will be an inequilibrium state. It was in equilibrium at that elevated temperature, but as you have suddenly reduced the temperature, this will be an inequilibrium state. So to maintain, go into a new equilibrium, the population from higher energy levels has to relax quickly to the lower energy level to maintain that new equilibrium at the lower temperature. But in that process, at some time, if you are able to create population inversion, then essentially you assume that the relaxation of population from different levels occurs at different rate. The rate of relaxation of energy from different levels occurs differently, giving rise to the possibility of establishing population inversion. For instance, suppose at some point population of this level at that elevated temperature was say 150 and this was 100, to satisfying Boltzmann distribution. This has a population which is less than this, absolutely fine. Now as you have rapidly cooled the gas, population here will start reducing and so population from here as well. Now suppose this relaxes at a rate which is faster than this. So at some time this population say has become 70. And over that time this population, this relaxes at a much lower rate. It has become 80. So that at that time population inversion does exist between this and this level. This level population is more than this. So if you now take advantage of a cavity, then this population inverted medium would eventually, would result in the possibility of amplifying light. Of course, at the frequency of light will depend on the difference of energy between these two levels over which the Lessing transition takes place. So how do you get such a situation in reality? Suppose you consider the case of a molecule and the various modes of vibration of a molecule, of the atoms constituting the molecule. You know that, let us assume a molecule M which comprises of n number of atoms. Then you already have studied, when you learned the method of operation, the principal operation of carbon dioxide laser, for which you actually learned some bit of molecular spectroscopy, you have seen that the number of degrees of freedom, the number of vibrational modes of the molecule which consists of n number of atoms is actually 3n minus 5. I won't go into detail of this. So if it is a diatomic molecule, then n is equal to 2. So the number of vibrational modes of a diatomic molecule will be 3 into 2 minus 5 equal to 1. So it has only one mode of vibration. If you take a triatomic molecule, so n equal to 3, so this means 3 into 3 minus 5, which is 4. So there will be 4 modes of vibration, 4 ways that the atoms can vibrate. These atoms which comprise this molecule can vibrate in 4 different ways. So it's 4 modes of vibration. Now, to simplify our understanding, we consider say just 2 modes of vibration, which are represented by these 2 ladders. This is the ground vibration, which will have 0 energy for both these modes of vibration. So I call it V equal to 0. that is ground mode. There is no vibrational excitation of modes in either of the two vibrational modes that we are going to consider. So one vibrational ladder is represented by these vibrational energy states. As you know that the spacing between the successive vibrational excitation energy states is nearly same, and this we call, say, the vibrational mode of vibrational mode 1, and there is second mode which is V2. This is the second vibrational mode, this is the first vibrational mode, and the quantum of energy required to excite one mode of vibration here is this much, which is delta E1, and quantum of energy needed to excite one mode of vibration in this is delta E2, and as you can see, we have considered a situation where delta E2 is more than delta E1. So suppose this is E0, this is E1, E2, E3, E4, and so on. So in the beginning, when T is very low, maybe close to absolute zero, all the molecules will be residing in the ground state. However, if we raise the temperature, then the population from this ground state will begin to go up into the higher energy levels, of course satisfying Boltzmann distribution. So these levels also would start getting populated in both these vibrational modes, following of course the Boltzmann distribution. That means never will be a situation where there will be population inversion. We just explained it is not possible. Now as you suddenly lower the temperature, as for instance by subjecting this hot gas to flow through a nozzle, a tiny orifice, so the gas would cool, and as the gas cools, temperature reduces, so this equilibrium will be disturbed, which will be an inequilibrium state. So the molecules will try to relax down from the upper energy state, it will tend to go to the lower energy states. So how does it occur? It occurs through a process called resonant vibrational energy transfer collisions. So what happens actually? Suppose I consider a molecule in this state, which is molecule M in state E3, and it may collide with a molecule which is in the ground state Me0, and the collision will result in transferring this vibrational energy. See, all these energies are equal. The spacing between the energy states, successive energy states, is the same. So this energy, this molecule will come down to this, that is, it will become Me1, and in the Me2, sorry, and in the process, this much energy will be absorbed by this molecule at the ground state and absorbing at and it will consume this much of kinetic vibrational energy, and it will climb up to this state. So it will be Me2 plus Me1. Then Me2 will collide with another ground state molecule, that is Me0, and Me2 will come down to E1 state here, from here to here, and this much energy will again absorbed by a molecule in M0, and because this energy and this energy is same, so it will climb up to this level. So it becomes another Me1, and already there exists Me1, so that makes it 3Me1. So you see, one molecule which was in the third excited energy state, through this vibrational energy transfer process by virtue of collisions, will result in creation of three molecules in the E1 energy excited state. Once it comes to this state, then it cannot relax anymore to this. That efficiency becomes much less, because if this molecule has to relax to the ground state, Me1, it collides with Me0, and if it has to become Me0, so it becomes 2Me0, then this vibrational energy has to be carried by this molecule as its translational energy. Translational energy. So long the transfer has been vibration to vibration, molecule is vibrating in this level, molecule is vibrating in this level also. Such collisions just took place very efficiently because energy was transferring from vibration to vibration. Here, the vibrational energy is transferring to translational energy. Whenever energy is transferred from one kind to the other, the process becomes extremely slow. Therefore, once the molecules, vibrationally excited molecules, have come down to the lowest vibrational state, it cannot efficiently relax to the ground state, because here the energy, vibrational energy, has to be transferred to translational energy. Basically, it will be realized as kinetic energy of the molecules, and this process is extremely slow. Now, the same situation will occur also for the other mode of vibration. The vibrationally excited molecules in this mode 2 also will quickly, through the vibrational resonant transfer collision, will come here. Once they come here, it will again not efficiently come down to this, and then because the vibrational energy that has to be transferred to translational energy is more than in this case, therefore this relaxation process is even slower compared to this, simply because more vibrational energy is involved here. And that is why there is a possibility that once in this mode, where the spacing, where the quantum of vibrational energy required for a vibrational excitation is more, then from this lowest vibrational state, the VT relaxation process is slower than in this case, because here the vibrational energy is less than this. Therefore, there is a possibility that you can strike a population inversion between this level and this level, simply because it relaxes very slowly compared to this. And that is how you can actually strike a situation where population inversion will exist when you rapidly cool a gas which you have previously heated, elevated its temperature. So this is the principle under which a gas dynamic laser operates. We will begin from this point the next class.